Okay, so we just handed back test number 2. Caitlin and I have decided to allow test corrections on this one as well. So as I've written over there, they're going to be due Monday, right at the start of class. You can earn up to 30% of the points that you lost. You can gain them back. So if you if you're staring at a 70 right now, for example, you could get up to 30% of the 30 points that you lost, which would be 9 points. So almost a full letter grade for people that are right around that number. In terms of working with each other, you are welcome to, but only verbally. I don't want people looking at each other's tests, and I don't want people looking at each other's test questions, but I think it would be great to communicate with each other out loud. You know, certainly like with the collective knowledge of everybody in the room, we have all of these problems right someplace in this room. So, so certainly work with each other, but don't look at what each other have written down. All right, so the last 2 projects are about data and rainbows, and I handed them out on Monday. Does everybody have the 2 projects? So again, the due dates are a few weeks from now. Looks like November 21 and 24. Okay, so the first one is due about 2.5, a little less than 3 weeks from now. Okay, so those are the last 2 projects that are math. There is one final kind of look back and reflect on the semester project at the end. And so that's that. Today we tackle a new topic called implicit functions. So let's dive in on page 5. And we'll jump up here to the top. Let's go to Haley for the daily summary. Okay, thank you. There's some general info about the tests and the projects right in between the summary and the demo there. So we're just going to jump down to 4, and you can read that text later on if you'd like. Let's go to Andy for 4.
For 4, find an equation for the tangent line curve x to the third plus y to the third equals 3xy 3 over q, comma 3 over q.
Okay, so here's the curve that is described by that equation. It's this thing here in red. I don't know how well it printed, but there's a blue, what's it called, that blue line? What would you call that line? I mean, it's almost tangent, but it never quite touches the curve. It's an asymptote. Normally the asymptotes we talk about are vertical or horizontal, but some curves have slant asymptotes, and that's what this one is. So, so this kind of little loop-de-loop probably looks very different for most of the graphs you've ever studied. And the fact is, most of the graphs we study come from equations that look like y equals. And this one doesn't look like that. It's got x's and y's all mixed together. And as a result, we get kind of strange things that look strange to us because we're so skewed to looking at y equals things. Is this a function? Why is it not a function? Yeah, vertical line test. So you can draw a vertical line that hits the curve more than once. In this case, hits 3 different times. So it is not a function. But it turns out we can still do calculus stuff on it. The point 3/2 is someplace right around here. And would you guys agree there is a tangent line to the curve at that point? Right? It doesn't bother us that it's not a function. There's still a tangent line, and you could imagine like a whole sweeping collection of tangent lines. There's one spot where you should recognize there's a problem in terms of finding the tangent line. Where's the problem? What's the problem at the origin, Kevin? It crosses itself, yeah. So is there a tangent line at the origin? There are 2 tangent lines at the origin. Because if you're kind of coming in down towards the origin that way, you get a tangent line that looks just about vertical, actually. And if instead you're coming in to the origin this way, sorry, that's not even on the curve, this way, then you get a completely different tangent line that almost looks horizontal. So we've got multiple tangent lines, which is a first for us, but at the point 3/2, we just have a regular old tangent line. So one option would be to solve for y. Because if you could solve for y, then it becomes the same as many tangent line problems we've done this semester. The difficulty is that most equations with x's and y's mixed up, it's impossible to solve for y. I don't want to say it's impossible in this case. You guys know, suppose that I gave you 1 degree less than this. Suppose that I said like x squared times y squared plus 2x minus 3y plus 7. What if I said that was the equation? You don't need to write it. But you could solve that equation for y because that is a quadratic equation in y, right? And you have a quadratic formula that you could use to solve any quadratic equation. So you could solve this thing for y. It would be quite messy because it would be inside of the quadratic formula, lots of things with x's in it. And just like there's a quadratic formula, there is a cubic formula. So it is possible to solve this equation for y. The cubic formula looks like the quadratic formula on steroids. It's much worse. And I don't happen to know it off the top of my head, so I could not solve for y without looking up that formula. But if I changed it to something just a little bit higher, like y to the 6th, all of a sudden there's no formula for a 6th degree equation. So solving for y is oftentimes difficult, if not impossible. So we'll say here, good luck. So we want another option, an alternative to this thing. So here's what we're going to do. We're going to take the derivative of both sides of that equation. And so the symbol for take a derivative of, one of the symbols we had was this, right? D over dx means take the derivative of whatever's in the brackets. So we've seen that notation before. And we're just going to keep in mind in the back of our head that that y is a function of x. Even if I can't in my mind get y by itself, I can still imagine that y is a function of x, even if I can't get that equation explicitly, right? So we just imagine y has x's all over it, but y is a function of x. So the letters x and y are inherently different things. X is the independent variable. It is just the lowest level variable. And then y is a function of x, even if I can't write down the explicit formula. So let's take a derivative of both sides. So I'm going to copy that equation again, x cubed plus y cubed equals 3xy, leaving a little bit of space in front because what we decided we were going to do was take a derivative of both sides, and it's legal to do that because we're doing the same thing to both sides. All right. So the beginning of this is going to seem like business as usual, and then things are going to change. What's the derivative? So first of all, this is a plus in between. The derivatives act nicely or not very nicely when there's pluses. Very nicely. So we just take our separate derivatives and plus at the end. What's the derivative of x cubed? 3x squared. Business as usual. What's the next symbol we write? Plus. Now we're looking for the derivative of y cubed. 3y squared. Business as usual. But there's a twist. 3y squared is correct but not finished. Because remember, in our minds, we were imagining that we've got y solved by itself. Even if I can't explicitly write down the formula, y has x's embedded inside of it. And so when I see this y cubed right here, I really need to think of it as some stuff with x's being cubed. Even if I can't explicitly figure out what that stuff is, there are x's buried inside of that y. And so if you had stuff cubed, what would the derivative be? 3 stuff squared times the derivative of the stuff. So we have correctly done 3 times the stuff squared, right? So that is correct. But it isn't done. We need to write down the derivative of the stuff. Now the stuff in this case is just a single letter. What is it? It's y. So what's our way of writing the derivative of y? Either dy dx or just a y prime. Either way. And so really the only thing that's new with this technique is that you take your derivatives of x as normal, and anytime you take a derivative of something with a y in it, you treat it like a normal derivative, but then you multiply by the derivative of y. You always tack on that dy dx because in our mind, y has x's inside of it. So let's see if we can play that game on the right-hand side now. So we're taking the derivative of 3xy. What rule do we need to use to find that derivative? Product rule, right? 3 times x times y. We can group this, we can either like imagine the 3 coming outside of the whole thing, or we can group it with the x if we wanted to. I'm going to imagine that 3 is outside, and so I'm going to write down 3 and then times whatever derivative I have to write down. So we're doing the derivative of xy. We've already dealt with 3. So the xy is a product. So we go first times derivative of the second. First is x times, what's the derivative of the second? It's y prime, or I've written it as a dy dx, so I'll be consistent. But you could just as well put y prime. Rest of the product rule says plus the second. What's the second? Y times the derivative of the first. What's the derivative of x? 1. And again, it almost feels like we're not treating these guys equally. It's like un-American what we're doing here. Like we're treating x and y differently. If it's just x, you don't do anything unusual. But if it's a y, it's special. Got to tack on that dy dx. Okay, so that is the end of the calculus. The goal here was to find the equation of the tangent line, which means finding dy dx, right? That's our slope. So we have some algebra to do right now because we need to solve for dy dx, which appears in red in 2 different places. So let's do the algebra. Okay, so the left-hand side, I'll just copy 3x squared plus 3y squared dy dx equals, right-hand side, we're going to distribute that 3. So 3x dy dx plus 3y. Okay, again, the goal is to solve for dy dx, which still appears in 2 different places. So the basic algebra technique here is to get everything with a dy dx onto one side and everything without onto the other. And if it's not clear why we're doing that, it will become clear in the very next step. So I'm going to shove all the dy dx's to the left. So I'll keep the one that's already there, 3y squared dy dx. I'm going to move the dy dx term from the right-hand side, so it'll go over as a subtract 3x dy dx equals, and everything without dy dx is going to go to the right-hand side, what was already there, the 3y, and then we're going to move the 3x squared from the left to the right by subtracting it. So again, everything with dy dx on one side, everything without on the other. And the reason that's a good technique is that we can factor out dy dx on the left-hand side because there is now a dy dx in every term, right? So we factor that guy out, dy dx times what's left in the first term? 3y squared. What's left in the second term? Minus 3x. Just copy the right-hand side. And the reason this equation is better than the previous ones is how many dy dx's are there? Just 1. And that's what factoring does. It takes multiple dy dx's and pulls them all outside, compresses them into just 1. And so what's the last step to solve for dy dx? Is divide by this stuff in the parentheses there. All right, so I'm kind of running out of space. I'm going to go below 5 here. So that's the derivative. For the first time, we have a derivative that contains what letter? Y. Right? Every derivative we've done so far has just had x or whatever the independent variable was. It's very typical for this implicit differentiation to involve y's. So if you wanted to, you could factor 3 out on top and 3 out on the bottom, and they all cancel. So let's do that just to make life a little bit easier. So y minus x squared over y squared minus x. So that's our derivative, which means that's the slope of a generic tangent line. We wanted the slope of a specific tangent line. At what point? Not at 0. 3 halves, 3 halves. That's what we wanted. It was a slope at 3 halves, 3 halves. So what are we going to do with those two coordinates? Plug them in. Brendan. Why would you want to do that? The goal was to get dy dx, and that's what we have. That's all we want. Yeah. So let's plug in 3 halves, 3 halves into this equation. So I think we've seen this, but our notation using dy dx is just something like this. That vertical line is our symbol for saying plug in this bottom guy. So we'll just do 3 halves minus 3 halves squared divided by 3 halves squared minus 3 halves. And I mean, you can do the calculations by hand or with the calculator, but the fact is the top and bottom turn out to be exactly the same, but in reverse order. So what's the value of a fraction when it's the same number, but reverse order? It's -1. Upstairs, we're looking at like 5 minus 2, and downstairs is 2 minus 5. So they're both 3's, but one of them is negative. So -1. Is -1 reasonable for the slope of that tangent line? Yeah, it seems reasonable. And so then if we actually wanted the equation of the tangent line, we can go back to this y equals mx plus b thing. 3 halves was the y coordinate, -1 was the slope, 3 halves was the x coordinate. And I think we get b is 3. So the tangent line is y equals -x plus 3. So I haven't done this on GeoGebra. I'm not exactly sure. You know what? Actually, I don't think it's going to work. I think that if I try typing in that equation, it's going to yell at me. Y cubed equals 3xy. All right. I think that GeoGebra is only equipped to handle equations up to power of 2. So I don't think it's not programmed to be able to graph this thing. One last option. X cubed plus y cubed equals 3xy. So unfortunately, I don't know how to use Wolfram Alpha to just have it draw tangent lines for us, but at least this way you will see that that curve is one that I'm not making up. It's actually one that is studied, and there's a little part of it that we saw. And apparently it's got some crazy stuff happening. All right. Okay, so let's just get readers for 5 and 6, and then we'll move to the activity. We'll go to Levi for 5.
If you have an equation, so it's y, say that the equation defined by how do we know that we need to use this technique? The equation x is y.
Good. Isaac for 6. Okay, so that's the key right there. Ordinary derivatives for x. Let's slap on a dy dx whenever you're doing a derivative of a y. All right, activity starts on the next page. Raise a flag if I can help.